This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right. Good afternoon. So this will be a short lecture. I will just talk about first summary of the subject, just to remind you of everything we've done, and then that would also help me sort of provide context for the control exam that I will talk about next. So, and that's it. So. That would be, yeah. So the student feedback website is open now, so please fill it in as soon as you can. I would really appreciate that. So any feedback would be very useful. So thanks for doing that. All right, so this subject actually covers quite a bit of material, and I want to remind you of everything we've done. It's a good recap just before the exam. So we considered both analysis and design or synthesis in the subject. So we started with ordinary differential equation models. So if you remember, we talked about the importance of assumptions when modeling systems. We presented a range of different examples. We also talked about another representation of a model, which is convolution model. We proved that the convolution equation actually holds for linear time invariant models. And then we also learned how to model systems using transfer functions. This was more of a revision of what you did in similar systems or other subjects that you did before. Then we learned linearization. So linearization was basically a method to simplify a nonlinear model by a linearized one around an equilibrium point. So it's a crucial step if you want to apply any of these methods to a given system. So linearization is usually a necessary step. So we talked about Laplace transform. We didn't talk about Fourier transform. I excluded this. It's not necessary. So we just talked about Laplace transform in this subject, and you saw its usefulness. I mean, it led to the concepts of like poles and zeros of a transfer function, which are really crucial for analysis and design. We introduced sensitivity functions. So in a closed loop system, in a canonical form, you would have a reference input. You would have several disturbances. You would have input disturbance, output disturbance, measurement noise. Now, these sensitivity functions explain relationships between pairs of input, or given input, and output. Right? So we considered outputs either to be the output of the plant or the control output, or in other words, control signal. All of these sensitivities are capturing the sort of different aspects of the sort of behavioral performance, or call it whatever you want. So features of the system. Features of the system are captured by these sensitivity functions. We then also learn how to obtain impulse and step responses of linear systems, and we also talked about transients, so overshoot, rise time, settling time, and also steady state errors. We also learned how to relate these objects or features of the step response to, let's say, properties of the transfer function. We learned how to obtain them from the transfer function and locations of poles, for instance, of the transfer function to overshoot, rise time, settling time. In the second part of the subject, we introduced the notion of frequency response. So you saw that whenever you feed as an input of a linear stable system, sinusoid of a certain frequency, in steady state, the output would oscillate at the same frequency, right, as the input driving frequency. But the amplitude and phase may be different. So this difference in amplitude and phase tells you actually how the model of the system distorts the signal in steady state. So input signal is plugged in, and then it's sort of distorted, well, through amplitude and phase sort of shift. So this then led to, you know, body diagrams where we were plotting how this amplitude and phase are related to the frequency of the driving input, right? And we also introduced stability margins using body diagrams, phase and gain margins, and all of these were based on the Nyquist criterion. So Nyquist criterion underlies most of the analysis in frequency domain. In today's lecture this morning, we saw yet another application of Nyquist when we talked about small gain theorem. Because small gain theorem guarantees that Nyquist will be satisfied robustly if some condition holds, right? And then we also talked about fundamental limitations to performance, both in time domain and in the frequency domain. In time domain, we talked about, let's say, how unstable zero would always introduce an undershoot, right? And in frequency domain, we talked about how body integrals are basically limiting what's achievable in terms of shaping sensitivity function. So we saw that if we reduce the gain of the sensitivity at low frequencies, right, then that will increase the gain of sensitivity at some other frequencies, right? So that's a fundamental limit which you can't overcome with any controller, any linear controller. So this was all part of analysis, right? But we didn't stop there. We also used all these tools for design, all right? So what were the methods that we learned for design? Well, root locus was the simplest one. So we saw how we can tune a parameter in your closed loop system to analyze locations of the closed loop poles. Typically, we thought about this parameter as being a proportional controller, but that's not necessary. That can be any parameter in your closed loop transfer function. You can just rewrite the characteristic polynomial in a particular form, like 1 plus, you know, the parameter times some transfer function, and then you can plot root locus for that. So we also learned how to design PID controllers and how to tune them using Ziegler-Nichols tuning schemes. And after that, we concentrated on controller design for second-order systems. So we related poles of a second-order system to overshoot, rise time, and settling time, right? So locations of poles were related to these features of the step response. And then we said, well, if you can place the poles of the closed loop in certain locations, then you can address certain specifications on performance for the closed loop system. And we saw also that second-order system, you know, is often used as a sort of rule of thumb for higher-order systems if you can ensure that the second-order poles, like second-order system poles or two poles, are dominant poles. And if all other poles are further to the left in the complex plane, they will be faster, and their contribution and response would quickly die out. So then this dominant pole design can guide us to use all the sort of things we learned about design for second-order systems and apply it to higher-order systems, right? We also saw the pole placement method. We saw actually that if your controller has enough parameters in the transfer function that you can tune, then you can place the poles of the closed loop system anywhere you want. The only requirement was that the plant transfer function was co-prime, so there were no pole zero cancellations in the plant. And if that's the case, then the controller that's 1 degree less than the plant dimension, so the plant has n poles, you know, the controller with n minus poles would do the job. But we do play with all poles and zeros in the controller to achieve pole placement. And you saw that Sylvester matrix solution. Sylvester matrix gives you what the solution, or inverse of the Sylvester matrix gives you the solution to pole placement model. We saw how to design internal model principal controllers. So they are the controllers that allow you to track a reference, let's say at a particular frequency, like a sinusoidal reference at a particular frequency, or even constant references, right, with zero frequency, or reject certain disturbance inputs at like certain frequency. So what we learned was that in order to achieve tracking of such reference signals or rejection of such disturbances that we can model in this way, you need to include the model of such a reference or disturbance within the controller transfer function and then stabilize the system. Right? So if you stabilize the system and the controller has that model of the disturbance internally in its transfer function, then you can track those references and reject those disturbances, right? So we also saw how to do some like feed-forward design. It was like a, you know, non-robust version of sort of achieving zero steady-state errors. And then in the end, we concentrated on frequency domain design. I mean, Nyquist was underlying all this as an analysis tool, but then in terms of design, we learned how to design lead compensators, lag compensators, and lead lag compensators, right, in frequency domain using body diagrams. So also this morning we were looking at performance, you know, and robustness, right? So we learned about small gain theorem, which gives you ensured robustness, and we also saw how any perturbations in the plant affect your sensitivity transfer functions, and typically different performance sort of characteristics of the system can be captured by the properties of the sensitivity functions, right? So there's quite a bit, you know, you learned quite a lot. You also implemented these things in the labs, and you know, you saw them working in some non-trivial problems, like inverted pendulum is not a trivial problem. So when you attach your inverted pendulum on a cart, right, on the Lego robot, you know, that's a really already quite a bit of success, right, to achieve, to do that. All right, so that's it. So that's what we've done. Now, exam. So exam, please check the date and place, you know, just to make sure, because I got 4 different versions of exam timetable from our secretary. So I think I picked the right one, but please double check who you sorry? Sorry, it's 8. 8th of November. Sorry. That's a big mistake. See, whoever is listening, so please, you know, turn up the volume. So people who didn't attend. Sorry about it. Good that you are actually. So this was the most attentive you've been. You know? so many people picked up this mistake. All right. So it is definitely a mistake. It's Friday. It's Friday in the first week of exam series. It's in the morning. It's in exhibition building, Royal Exhibition Building. It's open book exam. All right. So actually, you know what I think I should do, just for the sake of all the people out there, because I would upload this. I would just correct it straight away. And All right. All right, this is better. All right, so calculators is standard stuff. You know, this is I just copied it from the exam sort of first page. Standard thing, 3-hour exam, 15 minutes reading time. All right. All material covered in lecture slides is accessible. Now, this exam will contain 4 questions, and it would be it won't contain these short. These are all long questions. When people ask me, okay, so which topics should you cover? Well, you definitely get, you know, linearization, equilibrium. You definitely get root locus. You definitely get Nyquist. You definitely get body compensation. You know, so it covers pretty much. And then within these, there's a lot of other stuff you need to know. Maybe in root locus, you need to do Raoult-Hurwitz. You know, in frequency domain, you need to apply Nyquist in different ways. So this will cover, and usually you're asked to achieve some steady state errors, or, you know, so it would cover quite a, you know, like in a balanced fashion, it will cover all material you covered. So all of these sort of highlights, right? These are the main sort of design methodologies we've learned. They would be covered in the exam. There will be some other things maybe, but pretty much everything in this lecture slides will be there. Okay. So the exam will be different. Like every year, you know, I write a different exam. Don't expect spoon feeding or sort of simply following a formula. Maybe some questions would be similar to what you've seen, but there will be definitely some questions that are different from what you've seen. Because I want to test your understanding of the material. This is not like 2 + 2 = 4, and I'm testing you for that. I'm testing you for your ability to design things. And this means that there are infinitely many correct solutions in many of these questions. There are infinitely many possibly like correct solutions. Because every design may be different, but they are all correct and they all satisfy specifications. Okay? So please try, when you are studying for this subject, try to understand. Don't just do drills when you do question and you solve and you hope that you will get in the exam the same question. You won't. Right? Because I'm not there, you know, this is not, if this was, for instance, signals and systems subject, where you are just doing the analysis, then that would be the case, right? You just are given a transfer function, find poles, find zeros, find response, so it's analysis. But this is design, right? So it will be different, okay? In terms of consultations, so I'm not here next week, right? So, but I will be making myself available 2 days in SWOT-back, and 2 days in week of the exam, just before the exam, all right? So, note that I included on Tuesday different times from our usual time. So forget about the usual time 3 to 4. So this is not on. I will have other meetings there, but these are the new meeting times for the last 2 weeks, just before the exam. Okay. So I do hope, and I normally do get quite a bit of interest. Now, please be patient. I mean, I will try to, on some days, I may have a meeting right after this hour, and I will have to go somewhere else. I will just have to lock my office and just leave. So if I don't manage to talk to you, come the next day. I will have on some days more free time, like afterwards, and I can sort of talk to all of you. I had situations where students send me angry emails and say, I waited for 3 hours and, you know, I couldn't, you know, get enough time with you or so. But that was the first time that I saw the person. So So, I mean, I'm sorry, I can't multiply myself, or, you know, I will do my best to sort of answer your questions as best I can, but there's sort of limited time, and I will do my best. But please be patient, because, you know, there will be a crowd. It's like Disneyland, usually, just before, you know, it's like waiting for the, you know, Space Mountain or something, right? So that's just housekeeping, or whatever's happening just before the exam. If you're interested in further studies, so there are a number of subjects. I mean, I didn't maybe even mention all. We now have all this airspace, you know, sort of control. So you have advanced motion control, advanced control systems, capstone projects. If you're interested in doing a PhD, you know, and you're interested in control, please talk to me. I'm interested to see. Sorry? All right, and if you know, really want to, you know, think how to use control engineering tools and become famous, this is actually the most famous control engineer. You may not know that, but Rowan Atkinson, Mr. Bean, has actually a master's degree in control engineering from Oxford University. So, see, this is also where control may take you. All right, well, that's all. Thank you very much for your attendance, and I wish you good luck with the exam. Questions, or is there, yeah?
About the saturation at the morning, could you talk more details about that? The saturation at the higher gain.
So you are talking about this morning's lecture?
Yes.
So, all right, so I'm just going back to, because we have time, so the question is, when controller magnitude, so you have a controller transfer function, you plot its body plot, and its magnitude sort of is high in some frequency ranges. I pointed out that this might lead to saturation. Well, why is this? Well, think about it. If the system or controller, input to the controller contains a signal of a certain frequency where controller has high gain, right? So controller characteristic, gain characteristic might be like this. If there is a peak in the controller gain at a certain frequency, suppose that you are hit by input disturbance at that frequency, right? Now, that would mean that that frequency signal will be amplified because there is high gain. When you pass this, you know, sinusoidal disturbance through the control transfer function in steady state, you know, you will get amplification, right? So now, because you have now a large signal, large control signal, the input signal is amplified. So potentially you can have very large control signal at the output of the controller, which is input to the plant. Now, this large signal might mean, well, you are requiring of your motor to provide 100 newtons force, and it, you know, in control algorithm, but your motor can only provide 50, right? So, and because of this high gain in the controller transfer function, right, in body diagrams, it is likely that you might hit saturation. It's not guaranteed. For some initial conditions and for some inputs, you may not hit it. But if the gain is high, it's likely. That's why you need to be sort of careful. You need to keep that in mind, because that might cause problems. I think you showed me this morning a video of, I think you showed me the video of your lab? Yeah, so the video was basically showing inverted pendulum, and it was oscillating. And, you know, someone was pushing it. It will go down, but it will again keep oscillating, right? So this is a nonlinear phenomenon, which might be due to some nonlinearities, including saturation. So if that's the case, if you're hitting your saturation, you might have a stable, let's say, oscillation like this. So this is different from oscillations that you find in linear systems. This is a purely nonlinear phenomenon, right? Stable oscillation, so is the oscillation which is such that if you perturb it, the system would go back to this oscillation. In linear systems, if you have an oscillation, think about a harmonic oscillator. Harmonic oscillator, if you push it, so you oscillate, but you perturb it, you will end up in a different oscillation because the amplitude will change, right? So you end up, you provide an input, you end up in a different state, you turn off the disturbance and it starts oscillating at a different amplitude. But what you show me is a very nonlinear phenomenon. That's a possible consequence of saturation. Yeah. All right.
Excuse me, is it accepted that we were given like unstable blunt control in the exam?
You can be given any plant. I mean, you are now versatile control engineers, and you can be given any sort of plant control. Yes.
Because in the examples, the compensated linked feedback, all the examples are taken stable blunt.
Right? Yeah. You might get unstable. Yes. Yeah. Any other questions? All right. Typically, I would give you plots. So look, I'm not testing you there whether you can, plot a function. I would rather test you on your ability to use plots to design something or to conclude something. So typically, I'm trying to give you as much as possible of the plots, right? Yeah. Any other questions? All right, so I'm sure I will see you just before the exam. So thanks for that, and good luck.
Actually, I still have one more. It is about this one.
Yeah.
It is about this one. Here. To make parts of problem of presenting a measure of noise. Why the? Because I want to say that the higher gain of here
Yeah,
is still the peak, right?
That's right. So
Okay.
know that controller, we have a unity feedback.
Yes.
So any measurement noise
Yes.
will enter the controller. It's really, reference minus output.
Yes.
But now if you have noise, minus output minus noise.
Okay.
So if noise is high frequency,
Yes.
it's not filtered at all, it enters controller directly. So any high frequency noise would hit you bad.
Okay. Can you repeat that? Any high frequency? What?
So you have reference signal, you have your controller, and you have output
Yes.
noise. This noise enters directly into the controller. There is no filter or anything in the unity feedback system. So if this noise has high frequency components, they would be magnified by this guy. Yeah, because the gain is high, large frequencies. Typically, noise operates in high frequency range.
But even. Oh.
The input into the controller is R minus Y minus N.
Oh.
So if N is high frequency, then there will be a component here due to that high frequency which will be magnified. Yeah. Okay.
Just quick question for the quiz, the previous quiz. So it said it's a nonlinear system and it has a linearization like this.
Okay.
And when it's applied to the system, the sinusoid input will have amplitude A, and the most correctly said that the output would be bounded for sufficiently small value amplitude A. I just confused about why it's related to the amplitude of the input.
Because the linearized model is only valid for small signals around the operating point. If you have large amplitude, that would take you outside the region for which linearization is valid. Linearization is approximating your. So think about it this way. Again, I want to. So if you have, let's say, a function which you are trying to linearize, this is basically approximating it in a line at a point. So this point would correspond to equilibrium, and this region is maybe the region where linearization is a good approximation of the nonlinear function. If you apply large amplitude, you will be getting outside this region. And in this region, you would have make big errors. So you might even destabilize the system.
I thought that it's like a specific like amplitude is not like because in my understanding like small amplitude means it's at a low region.
Small amplitude, no, small amplitude. I'm talking about equilibria and staying close to the equilibrium.
So it's like from this point, and small amplitude is around just around this point.
No, I'm saying, look, this is the input.
Yeah.
This is the input, and this is the output. This is a static system. So this region would be the region which this linearized model. So linearized model is this tangent, described by this tangent. So this is your equilibrium U star. So for any input, which is basically any input U minus U star, smaller than some small number delta, which is basically, this is your U star plus delta, this is your U star minus delta, right? So if your inputs are here, then the error between the linearized model and the true system is small. But if I start applying inputs which are like this, amplitudes are like this, then here you have huge error, and you have no idea what the true system would do.
Yeah. What I thought is I thought the amplitude A is direct to kind of like U.
Yes.
So it will I just thought it will vary from the zero and to
No, that's frequency.
but it's
So when we were looking at sine omega t plus phi, it's the frequency that varies between 0 and infinity. Here I'm talking about some finite amplitude. I'm talking about this.
So the horizontal is the input.
No, it's just, so I just telling you, this is a function how, but if I apply this input, that will be the output. This is just a static function. Now, I can make input time varying, and that's the question here.
Time varying.
Right, so the input can be time varying, and then the output will be time varying, but they will be always related to this function. Functional relationship to the model.
So it's just the small region is just around
Around equilibrium, that only around this point, you would have that the linearized model represents the nonlinear model.
All right.
Well.
Yeah.
I didn't define stability margins, in detail for cases when you have, multiple, let's say, poles. If you have an unstable guy like this, you will just have, like negative gain. But, have a look at Ogata's book.
对，因为我知道它这个
Sometimes you may have multiple crossings of the negative relaxes.
但是你进的 amplitude 是相当于你进了一个 A sin 所有的一个 sin 东西，你为什么它是
You have multiple candidates.
That's why I asked.
So in those cases, these measures, margins, are not a good measure of robustness.
So I can't apply.
Well, as a rule of thumb, you can, but have a look at Ogata. I would say, if you want to learn, then yes, have a look at Ogata. Yes. So the way not really for stable plants. It's really more for the plants that how can I say this? These sort of stability margins can work well for unstable plants, but the definition is tricky. So then defining it more carefully is important. And this simple definition is not going to tell the full story. So an appropriate generalization would be still applicable, right?
Could you look at this one? I think
want to achieve good tracking of RAM preferences.
Yes, the RAM signal should be, because the correct answer here should be at least minus 40, right? And I don't think the 2 is
So
wrong.
let's see.
I think it is some.
But what's the question? Suppose it's achieve good tracking of RAM preferences.
Yes.
All right. Design strategy.
I think it's minus 40 for the RAM signal.
Yes, you're right.
And the second is correct because it have to, if it is good checking, it have to make
Yeah,
it
you're right.
very large open loop, right? And also say that. And I don't know why this one is, actually this one is also correct, but it is not suitable for this case, right? This one is also needed.
Open loop transfer function is sufficiently large at large frequency.
Yes, to
This is-
reject the noise.
Yeah, but no, we don't need, we don't need it for tracking reference signals, RAM preference signals.
Okay. So I think that the answer is wrong. Right?
Yeah.
So
It should be
two.
minus 40.
Yeah.
Yeah.
And also, just now you talk about the saturation. Because my understanding is, because the controller here have a peak, right?
Yep.
Or maybe the peak is broader than this one. And if we have an input located quite near the peak here,
Yeah.
and input in, it will
Yeah, but
hit
this
the
also,
saturation.
look, this is all above 0.
Yes.
So this means that controller is amplifying high frequency signals. This is a problem. The smallest amount of noise will be amplified. That's not good.
Yes.
That's not good.
Okay.
So that's also what I was talking about.
Because in experiment, we want to achieve the small steady state error. We bump the K to very large. I think that might be the problem of many people. That's why they shaky.
Right.
And also due to the K has to be very large as it is the unstable
But you see, large
model.
K leads to large control signals, which might lead to
I understand.
saturation, which might mean that you have a limit cycle.
So is it good option to choose a K that is very close to 0, the final K? I mean the KP. The
Well,
KP.
you can't just look at one thing at a time, right? It depends on the full model, right?
Yes.
So if your controller, so it all depends on how you pick the closed loop poles. Like
Yes.
if you, in control, advanced control,
Yes.
I teach optimal control.
Okay.
So in that subject, we do not pre-select closed loop desired location of poles,
Okay.
but we just solve a cost, and we say we minimize a cost.
Mhm.
And we indirectly do pole placement by minimizing more meaningful cost.
Okay.
Here, it's a bit tricky because you sort of need to think about root locus.
Mhm.
When if you have,
A pen.
it really depends on so this morning I was teaching in advanced control. Suppose you have a double integrator.
Yes.
What's the root locus for double integrator? It's just that, right?
Yes.
But if you want to stabilize this, well, how do you do it? Well, you could do it with PD control.
Okay.
If you include a stable 0,
Yes.
right? What will be the root locus? Well, this will be part of the root locus, this won't. So you will have something like this, right? And one of these would go here, one of these would go here. So you see, it wasn't just about the gain, it was also about selecting the right sort of 0, which then determines the closed loop pole location. So talking just about the gain is not, but in some plants you can just talk about how high gain might be detrimental. And we talked about it when we considered root locus. We said high gain might destabilize, right?
Yes.
So,
Thank you very much.
But the problem here for my workshop is that I guess for high gain I get stability because I think in close loop I have 2 on the right hand plane. High gain, that pole moves to the left, but I get
well, but you
saturation.
see, what I just showed you here, maybe cranking up the gain is not a good strategy. Maybe you can be cleverer about lead lag compensation, because lead and lag compensators introduce both poles and zeros, and that typically changes totally what you are able to do with even low gain, right? So it's much more involved than just talking about high gain.
when you add lead lag, you add the same amount of poles and zeros. Don't you want to add a new zero?
But you can put them in locations that are convenient for design. You can put them in locations that are convenient for design.
Yeah, that's right. Yep. And
So,
also,
I talk to them because you jump
I
in
talk too much,
always.
yeah.
No, you jump in. So you have to talk to them first.
Sorry. This is one of the creases. It's want to reject the step input disturbances and track ramp inputs. So the answer is plan is type 1 and control is PI. I'm thinking that if the plan is type 2 and the controller is P, the open loop transfer function kind of the same.
Yes, but it depends actually. So what I suggest that you calculate the complementary sensitivity and transfer function, and also calculate the output sensitivity transfer function. So just to understand how, and then steady state errors to the input disturbance or output disturbance and reference. You will see that there is a difference. Although the open loop transfer function is the same, it does depend on where the input enters.
Okay.
So reference inputs enter before the controller, but disturbance inputs enter either before the plant, between the controller and plant, or at the end of the plant. So it does depend on where input enters, whether you would really achieve zero steady state error or not. So typically, if controller contains the model of all references and disturbances you want to track reject, everything will work. But if you're talking only about references, then if plant has the reference model in it, then controller doesn't have to. But for disturbances, controller would have to have it. You can just do these calculations on